Eric Bergshoeff to present a talk about non-relativistic limit of general relativity by video, I suppose. Please.
Yes, hello. Can you see me?
Yes.
And can you hear me?
Yes, we do.
Well, I'm happy to give in some sense my talk live, because giving it with a pre-recorded thing is a bit weird to listen to your own talk. I understand I have not much time, and I was asked to give a summary of my presentation. And maybe that's nice, because I'm a physicist, and my formulae are slightly, and my language is slightly different than yours. So if I can say in words what I wanted to talk about, maybe I can convey more of the spirit of my talk. So my talk was about taking non-relativistic limits of general relativity. And if you follow a course on general relativity, we all learn in a physics course how to take a limit where you start from general relativity and you end up with Newtonian gravity. But that limit is a very special limit. It's really produced to get the Newtonian gravity, which is the gravity we use to describe our daily life. But it's a limit which makes all kinds of extra assumptions. It's not just a non-relativistic limit, but also a limit where you take weak gravitational fields. And so it's a very special example of a non-relativistic gravity theory. And what I would like to convey in my talk is that there is a much wider class you can take limits of general relativity. So there is much more hidden at the non-relativistic level in general relativity, and that is relevant if for people trying to interpret astrophysical observations, because often, for instance, to calculate the merge of two black holes, to use general relativity is too difficult. So people use then what's called a Poisson Newtonian approximation. So they first approximate the whole thing with Newtonian gravity, and then they calculate corrections. But the point I would like to make is that the fact that you take Newtonian gravity and then start calculating corrections is in some sense a choice. But so you can make more general expansions. And the point I would like to make is that for other situations, it is useful to take different limits of general relativity and then starting to expand. And so now, but what one thing you learn if you do this research is that taking a non-relativistic limit is really not an easy thing. The way it is usually done is that suppose you start from general relativity, it's almost like a Wigner-Neumann contraction of the Poincare algebra. You first redefine all your fields with a parameter which is often called the velocity of light, c, and then you take the limit c to infinity. That's a bit sloppy because c has a dimension, and you can only use for a contraction parameter a dimensionless parameter, but you can always, the idea is that c always occurs there where it gets the dimensions right, and if you want a dimensionless parameter, you can always redefine c with an extra parameter which is dimensionless. But at the end of the day, effectively what you take c to infinity, and c disappears. In Newtonian gravity there is no c. But the problem is that you see your relativistic theory has quite different properties from your non-relativistic theory. To give you two examples, the relativistic theory has particles and antiparticles, and your non-relativistic theory is only particles. Another thing is that your relativistic theory has a nice Riemannian geometry with one metric covering the whole of space-time, but your non-relativistic geometry is degenerate. In fact, you need two separate metrics to cover the whole of space-time, one for the spatial directions and one for the time direction. And what is also important is that in general relativity, mass and energy are similar concepts, are identified, whereas in a non-relativistic theory, mass and energy are two different concepts. So that means also that with that you associate two different neutral currents, which means that, in fact, explains already, if you take the limit at the level of the Poincare algebra, you don't get the Galilei algebra, which you would expect on the base of a usual Wigner-Neumann contraction, but you get the Bargmann algebra. You get an extra central extension that's related to the fact that mass and energy are two different concepts. The problem now is that if you take this limit, that if you take c to infinity naively, then you get divergences. But already you see in the metric, if you expand the metric, then the time directions and the spatial directions have a different powers of c. So one of them diverges, you get divergences. And the whole trick is now in defining these non-relativistic limits is to take care of these divergences. And recently some tricks has been invented in which you can remarkably creatively get rid of the divergences and take different limits. So one way, for instance, if you if you want to get, so in school books, people always explain how to get a Newtonian gravity from general relativity. But if you want to really have a nice frame-independent formulation of Newtonian gravity, which is valid also for strong gravitational fields, you really should get what's called Newton-Cartan gravity. And the way to get that, and that's really the non-relativistic limit of general relativity without any more assumptions. So it's much nicer to take that limit, and then always after that, you can assume weak gravitational fields. And to get Newton-Cartan gravity out of general relativity, you have to add to general relativity a vector 1 form, which has to do with the fact that there's a neutral charge for conservation of particles and antiparticles. And then if you take the limit, you express everything in terms, you redefine everything in terms of this parameter c, the velocity of light, the c to infinity. Then what happens usually is that the things like the affine connection or the Christoffel symbols, they blow up. And people don't like that, and then they set the divergence equal to 0, which is a constraint on the geometry, which in fact is what we call a zero torsion constraint, which is nice because the zero torsion constraint identifies your space-time with a Newtonian space-time. But what we have learned is that in some sense you have to be very careful. After all, the metric also blows up, the Christoffel symbol can blow up. What you would really not like to blow up is the action or the equations of motion. If you do that, then you can take more general limits, provided you combine general relativity with certain matter contents. And then you can arrange it, and that's one thing we learned, you can take limits so that we get not just Newton-Cartan gravity, but also with non-zero torsion. And so that's not quite a Newtonian space-time, but it's one in which you still have an order of events, one thing after the other, but not an absolute time. So if two observers travel from one event to the other event, they disagree about the time difference depending on their path. But you can get non-zero torsion. So that's one generalization in the limits you can take. Another generalization you can take is that you see, although particles and things like cosmic strings, they couple to general relativity in a unified way, that's not true for non-relativistic gravity. So we all know how to couple the Newton potential to a particle, but we don't know how to couple a Newton potential to a string, a cosmic string. For that, you really have to use, what you have to do is not add just a vector to general relativity, but a 2 form, because that's the thing that couples to a cosmic string. And then you can take a limit, and then you get a version of Newton-Cartan gravity, which has what we call a foliation, a geometry with a foliation, codimension 2 foliation. So Newton-Cartan gravity is a geometry with a codimension 1 foliation, appropriate for particles, but for strings you need a geometry with codimension 2 foliation. For instance, if you want to approximate cosmic strings with non-relativistic gravity, you have to use these geometries. So these are 2 examples that you can go beyond Newton-Cartan gravity. You can get non-zero torsion by adding matter to general relativity and then arrange a kind of subtle cancellation of divergences. Or you can also consider extended objects like cosmic strings, but then you have to go to geometries with a codimension 2 foliation. And these things we have been used recently also to take limits of string theory. So that's a theory to describe quantum gravity. And then you get non-relativistic string theory, and that's used these days to describe things like non-relativistic quantum gravity. The question is, for quantum gravity, do you need special relativity, yes or no? I mean, is there also a version of quantum gravity without special relativity? And that seems, well, you can go a long way in that. And so I think at some point I should stop because I understand you have to close. But the message of my talk is that taking a non-relativistic limit of general relativity is much more subtle than you think. And there are many possibilities. So Newtonian gravity is just one way, but there are many other non-relativistic gravities you can get. And these have found recent applications both in the context of gravity, which I discussed in this talk, but also in the context of condensed matter physics, where people they like to couple quantum field theories to non-relativistic gravity as response functions. So there's a lot of fun to get in this field of taking limits of general relativity. And I think it's more or less 7:30, so maybe I should stop now. So if there's any question, last minute question, I'm happy to answer. And sorry that I'm not in Paris.
Thank you very much.
Yeah, I have a question here.
Okay.
We have a time for a question.
One question.
One question.
Yes. All right. Okay, great. So yes, I'm also participating remotely. So my reading of the physics literature of this Einstein-Cartan theory is that there they assume a metric compatible connection that carries torsion. So in other words, this connection is not the Levi-Ceyda connection. It differs from the Levi-Ceyda connection in that it carries torsion, but nevertheless, it is still metric compatible the covariant derivative of the metric is still 0. So that is one of the, I think, the way they go about studying, trying to build this Cartan, the torsion theory for gravity. What I wonder is that if you go away from that restriction, just look at say dual connections that may not be metric compatible, that maybe still carry torsion. Yeah, there is this possibility, and we actually look into that to see the possibility of constructing dual connections that carry torsion, and this is possible. So, but we haven't looked into how to link it with the physics. So I'm an information geometer, so that's something just for your consideration.
Well, so indeed, you can make, of course. Well, first of all, we usually in our field work not with metrics, but with vierbeinen. That's easy if you want to relate to an algebra, and you certainly can impose a metric compatibility condition. But what happens is that it doesn't allow you to solve for the affine connection completely. So in general relativity, if you impose metric compatibility, you can solve for the Christoffel symbols. But in these non-relativistic things, you get a part of the Christoffel symbol which you can't solve. Well, that's related to the fact that that part is related to the central charge of the Barking algebra. So there's an extra, in the solution, there's an extra vector field which is related to the central charge of the Barking algebra. And that's part of the solution of your connection. You can't, so if I talk in terms of spin connections, you can't make a dependent expression in terms of just a vierbeiner, because it doesn't transform like a Lorentz gate field, because the points that you have less boost, the boosts are different. So you need extra vector fields to make a nice thing. But torsional, certainly, if you take a null reduction, for instance, general relativity in 5 dimensions, you do a null reduction, then in general you get Newton-Cartan with torsion. So it's in that sense, that's another way to get torsion in a natural way by null reductions.
Yeah, but so sorry, let me just jump in this. So I understand. So once you carry the torsion, you cannot have a holonomic frame. So therefore, you cannot have the basically a coordinate frame. This will be a non-holonomic frame. So which is natural. You have vector fields, and you do the frame fields. You have and frame fields. But what happens for information geometry is that you can have a way to have a pair of connections. One of them is torsion free, and the other one carries torsion. So the one that is torsion free, and you can still have a coordinate frame with it, it's a dual connection that carries torsion. So this is an interesting situation that what I think information geometry may provide some useful tools to study.
I think okay, we should stop. But one last remark is we should be very careful what we mean by torsion, because by torsion, I really mean not just adding a covariant tensor to the affine connection, but really a constraint in geometry of the space-time, that the curl of the clock function is 0. That's what I mean by zero torsion. And that is the definition.
Torsion tensor. I just meant torsion tensor. So anyway.
Yeah. So okay.
Torsion tensor.
Yeah.
All right.
Thank you very much.
Okay, so thank you. So see you tomorrow for the last day of the GSI conference. And thank you to you, Professor. And also people have a copy or hard copy of the proceedings, so they can read your paper, which is very interesting. I read it during your presentation. And I invite the attendees to read it carefully. Thank you.